Right. Let me just check. Please start the recording.
Yes, sir,
Mm,
I've started.
Thanks. So today we are going to start a very important topic in networks, which is called routing. It is such an important topic that many times, you know, when somebody says computer networks, right, or communication networks of any sort, routing is one of the first things that comes to the mind, right? It's a very important, very important topic. Okay. So we need to understand few fundamental things, and then we will go to two very important mechanisms for routing in the internet. Okay. So and today we will not be able to cover the entire routing. So it is going to go to the next week, and next week probably an hour or two will be required before we can complete routing. So let's get started and try to understand what routing is all about. Hmm. So, so far, you know, if you think, right, so if you think of the computer networks, so let us take this example. Let us take the example of, let us say that, you are connected to your computer from the IIT Kharagpur LAN, right? So most of you, I believe, by now are already in the campus. Just think of it this way, that you are connected to your computer uh, in the IIT Kharagpur network, right? So what happens? What happens is that you want to connect to, you want to send some message. Think of it this way, that you want to send some message to another computer which is located in some other network, right? It could be, let us say, a network in Europe, a network in US or somewhere, right? So you want to send some packet to another computer which is located in another network. So if it was within the same network, right? Then so when I say same network, I mean that, from IIT Kharagpur one computer to another computer, if you are sending, right, and if it is the same LAN, what are the mechanisms in place to connect these two computers together, right? So this is something that we covered when we talked about Ethernet and all, right? Now, if the distant computer is not in the same local area network, then the packet basically goes through something called the router, right? So the router kind of, so there are actually, so far you have already come across, like, there is something called switch, there is something called router, there is something called gateway. We also talked about bridges, hubs, and so on in a previous class, right? So by now the difference between these, but let us try to understand what is this router. So this router, what it does is that one network to another, basically, if you have to send a packet, basically these routers act as kind of the gateways, right? So they act kind of like the sentinels, which will take the packet from the inside of a network to outside. Now the question is that this is fine, right? So what you can have is two computers, you can connect and you can have a router in between. Uh, but the thing is that in the internet, if you think of the internet as a collection of different nodes and which are connected together through different edges, like, the graph representation of the internet, if you think of, then so these routers could be many in between, right? Which implies that in the graph that you have abstracted, you can have multiple different routers, that means multiple different nodes through which the packet from the source to the destination is going to traverse. Now, you see that if you are thinking of the graph representation of the same, then there are many different possibilities of traversal of the packet from the source to the destination, isn't it? So if you think of the, if you represent the network or the internet as a graph, between the source and the destination, there could be many different paths, right, that a packet could traverse. Okay. Now the question is that which path you are going to take. So this is where basically these routing protocols and the corresponding algorithms can help decide which path the packet is going to be taken, right. So this is basically the essence of these routing protocols or these routing algorithms, some of which we are going to touch upon today, and the rest we are going to do next week. But today we are going to look at some of these basics of whatever I just said. So routing is a phenomenon which basically takes place in layer 3. Okay. So you know what is layer 3? What is layer 3? Network layer, right? So this is a process in the network layer. Okay. So as I said that between a source and a destination, host or a network, basically one can use these routing protocols to find the optimal path to deliver a packet. Okay. So this is the essence of routing, and there are many different things that I have mentioned for you. So I am not going to go through each one of them in detail, but I leave it to you to go through at your leisure in your hostels. So let us try to understand that now the thing is that how can you execute these routing protocols and their corresponding algorithms, because ultimately if you have to execute or if you are thinking of the internet as a graph, right? So you need to think like which node to, so what is the source node, what is the destination node, and to compute like what path it is going to take. So you need to basically execute this routing algorithm. Now these routing algorithms, they are going to be executed at the routers, right? And each router basically needs some previous knowledge of the networks to which they are directly connected. Do you understand? So basically I do not need to have a global knowledge, right? I mean, it is possible to get the global knowledge, but basically, so what I need to do, so there are different routing protocols, but typically, so what you are going to do is that as a router, you need to find out, to which network or networks you are connected to. That means the router is connected to. So what this routing protocol is going to do is that it's going to, if it has received a packet which is destined to some other destination, then it is going to first determine through which interface of it is going to send through, so that the packet can reach the intended destination node. And mind you that intended destination node may not be situated in the network to which the router is directly connected. So basically, there are different complex mechanisms in place, but basically, what the router tries to do is by sharing with the immediate neighbors, etc. So it tries to gain indirectly, it tries to gain the knowledge of the network topology. It tries to gain the knowledge of the network topology. Now, so what are the goals of routing protocols? There are different goals. Optimal routing is one. That means that given the source node and the destination node, what is the most optimal route to be taken? Now, when I say optimal, the question is that in what sense we are talking about optimal? Is it the physical distance? Is it the time that it takes from the source to the destination for a packet to traverse? Is it the signal strength that we are talking about? Or is it something else? So this is where there is something called the metrics, right? Routing metrics basically, which can help in determining the optimal route. Okay. So optimality is one of the most fundamental criteria of the design of routing protocols. And this is where, based on these different metrics, like the distance, the next hop, the number of hops, the distance, the physical distance, the number of hops, the delay, the signal strength, etc. Based on all these different types of metrics, basically these different routing protocols, they have come up with their own different ways of handling this quote unquote optimality. Okay. Now, like this, actually, there are few other criteria that are also considered by these routing protocols. So, one of the other ones is, for example, stability, right? So, stability means that in a network, so these networks, they change dynamically. So, there are different events that can happen in the network, and many times these events are unforeseen. So, for example, that the network runs and all of a sudden one of the links basically breaks, or one of the routers, it becomes dysfunctional. So, one of the key criteria of these routing protocols is that can it take into account this unforeseen circumstance, this event, and try to find an alternative route which basically bypasses this failure, right? So, how far a particular routing algorithm or a protocol is able to adapt to the changes in the network events such as failures and other incorrect implementations, etc., is the property of stability. So, like this, actually there are other properties, for example, the ease of use of the protocol, the flexibility with which these protocols are able to adopt different features, etc., the convergence of the network, right? So like this, actually there are all these different other all these different other goals of these routing protocols. So please go through all of them. These are texty, and I do not want to go through all of them myself. Rather, I would focus more on the concepts. So this is for you to go through yourselves. Okay. Now, so metrics. So I was talking about these metrics. So these routing protocols, they adopt some metrics, right, to determine, like, based on what you are going to determine the optimality of the routes between the source and the destination. So for this, basically, again, different criteria are there. For example, the number of hops, which is called the hop count. Remember that this is a technical term, hop count. So the number of hops. Hops means what? One node to another is one hop. That node to the next hop is that node to the next node is another hop. So like this, basically, these are called hops. Okay. So hop count is a metric. Then link utilization, so the different links, are getting utilized, because when you are sending packets, etc., so part of the links, the bandwidth, etc., are all utilized, right? So based on how much these links are utilized at a particular instant of time, you make the decision about which link or alternate links through which the packet is going to go through from the source to the destination. Okay. Then there are different other things like, the speed, the network delay, path reliability, path bandwidth, and so on. So like this, actually there are many different metrics that the routing protocols in the literature, they adopt. So irrespective of what routing protocol we are talking about, we have to keep in mind that these routing protocols, when we are designing, or somebody has designed, they have to ensure that they do exactly what they are supposed to do. So the correctness is important, the simplicity is important. We do not want to use a very complex kind of mechanism, right? Robustness, so even if there are some failures, some faults, etc., the protocol should be able to still handle that and should be able to work. Stability, I already mentioned. Fairness, optimality, efficiency. Efficiency means what? One of the efficiency criteria is the overhead. So how much extra packets you need to send, or extra information you need to send, on top of what exactly you want to send between the source and the destination nodes, right? How much extra information? Because we have seen already that, if we have some data to be sent, the payload, right? In addition to that payload, we also need to send some control information, right? So so the headers are added with different additional information, etc., etc. So like this, you might be sometimes piggybacking some additional information like acknowledgements, etc. So how much extra information, so compared to the actual information that you want to send, how much extra information you need to add as part of the execution of that particular routing protocol. So these are some of these different desirable properties. So forwarding is one of the fundamental methods for sharing the information that I talked about between different networks. Okay, packet forwarding. Now here in packet forwarding, the packets are transferred from the source to the destination, which are typically located in two different networks, right? So when you issue a command or send a message to a non-local interface, your system forwards those packets onto the local network, and the interface with the destination IP address that is specified in the packet headers, they then retrieve the packets from the local network. So this is basically the way, the core of how basically these packets are forwarded. If basically the destination is in the local network, things are simple, but if they are not in the local network, then the packets will have to be forwarded, right? Now, how do the packet processing takes place? So this is what I was telling you yesterday also. It is called the longest prefix matching, right? So this is, let me just read these steps over here. So routers are going to use the IP prefix for processing the IP packet, and yesterday I told you the prefix and the suffix part, right? So the prefix is basically that /n, that many number of bits, and 32 minus n is becomes the suffix. Recall from yesterday whatever I said. So this IP address basically has the prefix and the suffix part. So routers, what they are going to do, they are going to take what is there in the IP prefix, and then they are going to do some further processing. Now this prefix, if you remember, this prefix basically is nothing but it corresponds to an aggregation of different IP addresses, because it signifies a particular network. So it's because it's the network part, right? So it is an aggregation of different IP addresses under that network, right? So for example, something like this 192.50.128.0/17, what is the prefix? The first 17 bits. If you write all of these in the bits format, right? So the first 17 bits are going to define the prefix as given over here. So 17 bits of the IP address to identify the address aggregation. The remaining 15 bits, so 32 minus 17 is what? 15. The remaining 52 bits may be either sub-aggregated or assigned to devices within the network that owns the prefix. So what does it mean? It means that you can the host part, so the suffix part basically, it could be like individual hosts, or it could be some sub-aggregated small networks. Okay, sub-aggregated devices basically. Okay, so the routers basically what they will do is they will look at the prefix, right? Then they are going to search the forwarding table to see if there is a match with the prefix, and then forward the packet to the corresponding next hop in the forwarding table. So it is going to be like this, that if you look at the forwarding table, so the prefix and the corresponding next hop is all going to be there, right? And here remember that we are talking about classless addressing. Now if the incoming IP packets prefix match several IP entries, because the prefix can match several IP entries in the table, right? It is possible, because here we are not talking about exact match, but we are talking about the first part, the prefix part, right? So it can match multiple IP entries in the table, right? So for example, the address is from 194.24.12.0 to no, forget about this. So 192.24.12.0 to 24.15.255. Okay, so from both of these addresses, they are going to match with the entries in the table. The prefixes are going to match the entries in both the entries in the table, right? So in order to handle this situation, so what is suggested is to use the concept of longest prefix matching. So wherever you have the longest prefix match, so you use that particular interface. So it is like this. So look at this example over here. So here basically we are talking about this longest prefix matching with the incoming packet's destination IP and forwarding the packet to the corresponding next hop. Now let us say that this is your table, right? So here you have the prefix and the next hop, right? So all the incoming packets in the range 192.24.12.0, this one. So all the packets that come between this one and 192.24.15.255, this, right? So in this range, right, all these are going to be forwarded through the interface B. So these are going to be forwarded through the interface B. Why? Because B has the longer prefix. So in other words, you can think of it this way, that in this table, as I was also telling you in the other context yesterday, that what you do is in the descending order of the length of these prefixes, you can order you can order these entries. So the first entry that you are going to get in this particular example is /22. So you match with that longer prefix, right, because this is more specific. Okay, so this is how basically this prefix, longest prefix matching is undertaken. So now let us proceed further and try to understand few more details. So I was telling you that there are different routing protocols that will need to be taken into taken help of in order to send the packets. Now how you are going to do it? So there are different mechanisms. One is called the fixed routing, flooding, dynamic routing, random routing, flow based routing. There are so many different, many other different strategies are also there. Okay. Many different other strategies are also there. Let us look at the essence of some of these. So let us look at the fixed routing part. So fixed routing mechanism first. Okay. So think of your network like this. So let us say that you have a network like this. You have all these different routers, the hosts, etc., etc. So the route in fixed routing is selected from each source to a destination host. From the source to the destination, it is selected. So let us say that from A to C, and once it is selected, right, that particular path of the route remains fixed, even if there are changes in the topology of the network. Let us say that from A to C, there are multiple different paths. So one could be like A1 to C, A1 3 4 to C, A1 4 to C, A1 3 5 6 to C, like that. There are different paths. So whatever be it, so in fixed routing protocols, basically once the route, the most optimal route, whether it is based on the number of hops or whether it is based on the utilization or whatever be it, once it is chosen, right, irrespective of whether there is any change in the network or not, topology of the network or not, you are going to use that particular path. So it could be the number of hops, it could be the minimum distance, right, between the source and the destination, whatever be it. So for this, basically two popular algorithms that are used are called the Dijkstra's algorithm and the Bellman-Ford algorithm. Now this is something that you have already learned in your algorithms courses. Okay, so you have already learned, what is the single source shortest path algorithms, right? So these are the single source shortest path algorithms, Dijkstra's algorithm and the Bellman-Ford algorithm, which are basically employed in these fixed routing protocols in order to compute the path between the source and one or more destination nodes. Okay, so fixed routing. So you see that if you look at fixed routing, right, it says that if you look at the routing table, so let us say that node 1. So node means these are like the routers, right? These are the routers. So if you look at the routing table of this particular router 1 or the node, then it is going to look like this. For destination 2, the next hop or the next node is 2. For destination 3, it is 3. For destination 4, next node is 2, like that. So what does it mean? So look at the node 1. So node 1 to node 2. Okay, node 1 to node 2. What is the next node to which it has to be sent? It is node 2 only. From 1 to 2, you need to send to the next node 2. Now, from node 3, from node 1 to node 3. From node 1 to node 3, same thing, right? So it's going to be sent to 3 only. Now, destination, if the destination is 4, then from node 1 to node 4, you need to take help of the next node, which is 2. So 1 to 4, okay, as per that routing table, you are going to take help of node 2. You are going to take help of node 2. So you see that you might now ask me the question that why, sir, why node 2? So 1 to 4 there is a direct connection, so we can reach faster. Yes, true. So it doesn't matter actually. I mean, although the number of hops over here is less than the number of hops through 2, right? But still, that is the hop metric, the hop count. Maybe this fixed routing protocol over here uses some other metric, maybe the congestion that is already there. So maybe this one will be faster considering the congestion compared to this direct link. So this particular routing protocol, it builds the routing tables in the individual routers according to the mechanism in place, and the entries are going to be filled in this particular manner. Is this clear? Any question? Any question? Okay. Now, so what are the advantages and disadvantages? The same thing, if you have things fixed and if things change over time, there is lack of flexibility. That's a disadvantage, right? So if there is some congestion, it cannot react to the congestion. If there is, so like this actually, any kind of inflexibility basically gets in these routing protocols, because these are fixed. It is determined a priori what the route is going to be. Now, but there are certain advantages also, right? So there are certain advantages. So these are like simple to implement. So these work well in reliable networks with stable loads and so on. So these are the advantages and disadvantages of fixed routing. There is another type of again a popular conceptually popular type of routing protocol, which is called flooding routing scheme, which is called flooding. Now flooding, basically, as this name suggests, so flooding is a kind of brute force or naive way of handling things. So flooding says that whenever you receive a packet, you do not really need to take care of the how a particular node is connected to the other nodes. That means in essence the network topology, what is the load in the different links, what are the different costs, etc. So those things you do not really need to take into account. So whenever you get a packet, you just send it through all the interfaces that you have. You mean through the router. So let us say that router 1, whenever it gets a packet, it's going to send through the interface 1.2, through the interface 1.4, and through the interface 1.3. So it floods through all the possible links. So like this, actually this process, it can continue. Yeah. So if once 4 receives it, it's going to again send it through all the possible routes. And like this, actually this is called flooding. So this is a very naive way, but again it works in certain cases very well. Okay. Now, so please go through these characteristics and all these things, blah blah blah. So these things actually advantages, disadvantages. These are quite understandable, but in order to save time, I'm not going through them in detail. But that doesn't mean that you don't have to go through. Please go through them in your hostels when you go through the book. Now let us try to understand the concept of selective flooding. Now pure flooding, what does it do? Through all the interfaces, it is going to send the packet out, right? But in selective flooding, it's not going to send the packet through every interface, every link. It is going to send through the links which are in the direction of the destination. So let us say that I is your destination. So the packets are going to be forwarded to only the links through all the links basically which are in the direction of the destination. Okay. So basically from E, for instance, you will be sending to you will not be sending to D, right, because that's in the reverse direction. So like this, basically the selective flooding, it floods, but the thing is that it doesn't flood to the nodes which are in the backwards direction, and that's quite obvious because backward direction basically, so it is quite unlikely that the packet will go through in an optimal way to the destination in the backward direction. Okay, that's selective flooding. Now there is also something called random routing, and as this term suggests, that which link, so let us say that we are talking about a router. So this router, it is connected to different nodes. The question is that which of these nodes it is going to go through the packet. So the outgoing link at the router in random routing is chosen randomly. So this is the name also, it says random routing. So randomly it is going to choose out of the links from a particular router, out of the links 1, 2, 3, 4, etc. It is going to choose, it is going to pick up one of these links randomly, and it's going to exclude the link through which the packet comes. So if the likely probabilities of choosing any link are equal, it amounts to choosing the outgoing link in a round robin fashion. So so basically, so if Pi is the probability of selecting the link I, if Pi is the probability of selecting the link I, and Ri is the data rate of a particular link I, right? So so this probability of selecting a particular link is going to be Ri divided by the sum of all of these data rates taken together, sum of all of these. So this is basically not J, this should be I think. So this is wrong over here. So this scheme basically could provide good traffic distribution where the sum Ri is taken over all the possible outgoing links. So this is basically the whole idea of random routing. Now this dynamic routing is interesting because this is kind of contrast to the fixed routing. In fixed routing, so the criteria are all fixed, the routes are all fixed, predetermined, etc. Dynamic routing, also called adaptive routing, basically adapts with the changes in the network conditions, basically the network conditions. So here basically so the routers basically they choose the routers they choose the path between the source to the destination, and these paths could change over time. So these routing tables obviously in fixed routing were all fixed, But in dynamic routing, obviously, because the paths could change over time, right? The routing tables are also going to be updated. This is a very important thing in dynamic routing. The routing tables are going to get updated. So now there are different advantages of dynamic routing. Obviously, availability, adaptability, like that. So all these theories are there. So please go through them. It's not like these are not important. It's not like that. So so you have to go through them yourselves to understand the advantages, disadvantages, etc. And I'm going to soon go through some important concept in routing. But before that, one thing I missed out, which let me just give you a little bit of understanding of how it works. I talked about IPv4, right? IPv6 basically I did not talk about. We do not really need to understand in too much of detail, but because I have talked about IPv4, let me also try to give you a little bit of idea about what IPv6 is. But it's going to be very shallow. You do not really need to understand in too much of detail, unlike IPv4. But let us try to understand the different properties of IPv6. So IPv6, basically this version 6, basically, you remember how the IPv4 header format looked like, right? So here IPv6 basically has a completely different header format, not like IPv4, right? So here basically you remember in IPv4 also there was the concept of the options. So here also you have the options, but these options are separated from the header, and whenever some options are required, these are going to be inserted between the base header and the actual data. So in other words, you have the base header, then one or more options, and then you have the actual data that it needs to be carried. So this is how basically this IPv6 packets basically so they are designed, right? So you have the base header, then you have one or more optional headers, right? And then you have actually these optional headers, not one or more, it should be 0 or more, right? So you may not have any optional header also. And then you have what? You have the actual data. So there are few other properties also of IPv6. For example, there is provision for different other options, etc. Which I am not going through because I told you that I will be very sketchy over here. We do not intend to go through IPv6 in too much of detail, but I just wanted to give you enough for you to know like what is in there in IPv6 compared to what was there in IPv4. So there is allowance for extension. There is support for resource allocation. So remember that in IPv6, the type of service field that we had, remember the type field was there, type of service in IPv4, that is no longer there in IPv6. But here actually there are two new fields that help in the handling of the resources. One is called the traffic class, the other one is called the flow table. So traffic class and flow table. Now now this mechanism it can be used to support the traffic such as real time. So what class of traffic, right? So so this traffic class, different type of classes of traffic, etc. So real time traffic like audio, video, etc. can also be supported, right? So then more security. So here in IPv6 basically you have added security mechanisms in place. So this header format basically looks like this, that you have the base header and then you have the payload, the actual data that is carried in the payload. So you have the base header, you have the payload, but in between you can have some optional headers. Okay. Now this base header, its header format is given like before. You have the source address, you have the destination address, but you remember that the source address and the destination address in IPv4 is how many bits? 8 into 4, 32 bits. However, over here it is going to be 128 bits. It is going to be 128 bits. So the source, both the source address and the destination address. Basically, these IPv6 addresses look like this, that you have a hexadecimal number, colon, another hexadecimal, like that, So you have, yeah. So you have IPv6 addresses which look different from IPv4. Okay. So like this, actually these other fields are also there, version as before, then you have the traffic class, flow level, payload length, like this, and also these different fields are there. So the corresponding ones are also mentioned over here. So these, the explanation of all of this, I'm not going through, but just you yourselves basically go through and try to have a feel for the difference between IPv4 and IPv6. IPv4, you need to really understand it inside out, as I said, and we spent quite a lot of time on IPv4. IPv6, not that much time we have spent, and you simply need to understand the overall concept and some of these properties, as I said. So you see that this is what I was telling you, that in IPv6 datagram, unlike IPv4, you not only have this base header and the payload, right, but you also have these extension headers. These extension headers in IPv6 come under this payload. So you have the header, you have the actual data that has to be sent, and this actual data, and in between you have these extension headers. Once again, this base header, you have these optional extension headers, and then you have the actual data that it carries. Now you see that there is this concept of these pointers, right? So basically, in IPv6, basically these headers, they have the next header field. So this next header basically points to the next header to which it is going to be chained up, it is going to be linked up. So as you can see from the base header, you have this next header field which points to this extension header. In this extension header, again you have the next header field which points to the next header, and this process basically continues. So this is how you are going to link up all these headers with the data. Yeah, so I think this is pretty straightforward. Comparison of IPv4, IPv6. So please go through all these theories yourselves, right? So not too much of concept over here. The concept I already told you. Now let us any question, students? Any question you have? Okay. So let us do one thing. We are going to. So I need to first unshare and share. Somebody has a question, I think. I see a raised hand.
Sorry, sir. Actually, I raised it by mistake.
Oh, I see. Okay, no problem. So everybody is with me, right? Acha, chalo. Now, so do one thing. Yeah. So let us. So let us talk about this unicast routing. Let us talk about unicast routing. This is a very important topic. So basically, we are still in routing. We are talking about a type of routing which is called unicast routing. Now remember that whenever we are talking about the graph representation of the network, or even if you are thinking of the network as such, then you need to send packets, right, from one point to another with the help of these routing protocols or algorithms. Now unicast routing talks about that from the source to the destination, how you are going to send the packets. So to a particular destination node, how you are going to unicast the packets that come, how you are going to send the packet to a particular destination node. Now there is also something called multicast. So in multicast, basically when a packet comes, it is sent to a group of nodes which are called the multicast group. So multicast group basically has to be formed in multicasting, right? So the packet, once it comes, has to be sent to the members of that multicast group. But here in unicast, basically you do not have that. It is sent to a particular destination node or a few different nodes. So this is called unicast, and in multicast to a group of nodes, a predetermined group, which is called the multicast group. Now, so can you all see my slide, right? You all are able to see my slide on unicast routing?
Yes, sir.
Okay. So now there is another type which is called broadcast. Broadcast means that you send it to all, it's broadcast, right? So you send it to all the packet basically has to be sent to all the different nodes. So here basically we are not talking about, in this course our focus is on unicast routing only. So multicast is out of scope, and same for broadcast also. So our focus is more on unicast. So let us try to understand what is this coming over here. Okay. Now this unicast routing. So here, as I said, the packet has to be sent from the source to the destination, and the packet is going to go hop by hop. Hop by hop, it is going to go from the source to the destination, and for sending it hop by hop, basically at every hop, at every router, you take help of the forwarding table. Okay, the source basically obviously doesn't need any forwarding table, right? So what it is going to do, the source, if it has a packet, it is going to deliver to the default router to which it is connected. And it already knows, because typically you are talking about a local area network, a host in a local area network knows what is the default router. So it's going to send to the default router if it has to go outside the network. The destination host basically also doesn't need any forwarding table, because it has to receive the packet from the default router to which it is connected in that local area network. Okay, so only the routers in the networks in between, all the routers in between needs to be in our focus, and this is where we will learn how we can build these routing tables or the forwarding tables. These forwarding tables or the routing tables are going to be installed, are going to be stored in each of these different intermediate routers, and these routers, they are going to refer to these forwarding tables to make the route decisions. And if you are talking about dynamic routing, these forwarding tables or the routing tables are going to be updated over time. So how it is going to be done? So I'm going to show you with an example shortly, but let's cover some theory first. So what happened? Okay. So remember that I was telling you that this internet, it can be modeled as a graph. So think of the graph representation of the internet. So if this is the internet, okay, so you have these, all these entities as the routers. So how many routers we have? 6 plus 1, 7 routers are there in this particular topology. Let us say that this is an internet work, right? Some internet, right? So here, why it is called an internet? Because between the different networks, basically, you have this interconnectivity, right? So that is how you have this internet. So if you look at the graph representation of it, so each of these routers are going to be represented as a node. Each of these routers are going to be represented as the nodes. Remember over here that so this router may be connected to some LAN, some local area network, like over here. So in this particular example, these two routers are connected to this particular local area network. Likewise, between these two routers, another local area network. Like this, actually, you could have thought about like a local area network over here. So whatever, so the question is that our focus over here in this graph representation for routing purpose, is that we are going to focus only on these routers and represent them as the nodes of the network. Now between these nodes you see that these are the different costs. So what does it mean? It could mean anything, right? So a cost of 2 units between the nodes A and B, that means the router A and B, a cost of 2 units could be anything. It could be the actual distance like 2 kilometers, it could be 2 milliseconds delay, it could be something else, the amount of residual bandwidth that is there between A and B. Like this actually you can think of any, so these are like just the abstract representation of the actual physical thing that you might want to model. Is this clear? So this is the graph representation of a network, of an internetwork, where these nodes basically represent the different routers and the links basically connect these different routers, and their link costs could represent anything like the actual distance, the number of hops, the number of the delay, the residual bandwidth, or anything basically. There are so many different metrics, and we have already seen, right? So little while back I talked about all these different routing metrics. So this could be any metric that you want to study basically. Now, so when we talk about this kind of thing, here we talk about something called distance vector routing. And in routing in the internet, basically there are two types. You can classify the routing in the internet to be of two types. One is called the distance vector routing, the other one is called the link state routing. Okay, so we need to really understand each of these in detail. What is distance vector routing? What is link state routing? So first let's go through some theory, and then I'm going to explain to you here. Actually this is a very important concept again, right? Distance vector and link state, very important, so you need to understand thoroughly over here. You cannot be sketchy over here. So this distance vector routing, okay, what is the purpose? Again, optimal route between the source and the destination. So what it does is, between the source and the destination, it tries to model, it tries to use the model, the graph model, to find out between the source and the destination, let us say between A and G, what is the least cost path that the packet will be taking. So whether A, B, C, G is going to be the least cost path, or A, B, E, F and G, or whether there are any other alternatives. So each node basically creates its own least cost tree, right, with the rudimentary information that it has about the net neighbor. So how it is going to do? So basically, A is going to use only the neighbor information, because every node basically in distance vector is going to share this neighbor information with every other node. So only the neighbor, immediate neighbor, only the immediate neighbor information is shared. So with that information, basically you try to build this least cost tree from every node to every other node in the network. So every node creates its own least cost tree with the information that it has about the immediate neighbors. And then this part is interesting. It is called the update part. So first you build this least cost tree, and then the update part basically. So these incomplete trees are going to be there. So these incomplete trees at each of these neighboring nodes are going to be exchanged with the immediate neighbors to try to complete the tree as a whole. So every incomplete tree is going to be completed through this exchange of information about the immediate neighbors. Okay. So in distance vector routing, the router continuously tells all of its neighbors what it knows about the whole internet. Okay. So so in other words, that A, it will tell that it will share with B that so if I have to reach the internet, let us say some other network, then I can reach the internet with certain cost. If I have to from me, if I have to connect to, let us say, G, I can do it with a certain cost. B also says that, you know, to A it can share, to C it can share, that from it to another node, you know, if it has to connect, then it can do so with what cost. So this information gets propagated all through, so after different rounds, right? And then everybody knows that from that node, so everybody knows the information after a little while. Every node has the information about every other node in the network, how it is going to connect to the intended destination node. So, so the whole idea is basically over here to use the Bellman-Ford algorithm, right? So Bellman-Ford algorithm is used in distance vector routing. So this equation is used to find the least cost, the shortest distance between the source and the destination through some intermediate node. Now, let us try to understand this concept in a little bit of more detail. Let us say that you are talking about the source X and the destination Y, and then you have three possibilities A, B, and C. The cost from X to A is Cxa, X to B is Cxb, and X to C is Cxc. And it is so you know, so the packet that comes to X intended for Y can take any of these hops, A or B or C. And now A knows what will be the cost to reach Y, right? So that cost to reach Y is day, the distance, for example, is day. This is dby, this is dcy. Now this is the general case with all these three intermediate nodes. Okay. Now if you have to update the path with a new route, what you need to do is that, you know, you can do it this way, that you know, so between X and Y you have to replace any of these paths with the path with the cost dxy. Now what is this dxy? Dxy is going to be the minimum of dxy and cxz plus dzy. So minimum of dxy, what is dxy? You are going to replace with dxy, which is going to be the minimum between this one and the sum of this cost plus this cost. So if that happens, then you replace this path with this particular path. So this is the you know, abstracted representation. I hope that, you know, everybody got it clear. So if not, I am going to show you very shortly how it is going to look like. So for now, so here actually I have given you an example, and in your slides, but what I will do is I have taken another example and I am going to work it out for you. Okay. So distance vector, please all of you, you know, so at your hostels or homes, please all of you work out yourselves, and very soon, you know, I will take a very quick break of 2 minutes and I'm going to come back and work it out for you. Okay. So let's take a break of 2 minutes and then we will continue with this. Okay. So let's take a break. Okay, so students, is my screen visible? This OneNote screen. Is it visible?
Yes, sir.
Okay, very good. So this is concept now. So let us try to understand this. So next week onwards, we are going to meet in the class, right? In the classroom. So this will make it easier for us also. So here, first we are going to talk about distance vector. We are going to talk about distance vector routing. So let us talk about let us consider a particular topology. Let us consider a particular topology. Again, this is something that I have borrowed from somewhere, not my own thing, but doesn't matter. Let me explain this to you, how things work. Let us say that this is node 1, this is node 2, this is your node 3, this is node 3, huh? This is your node 4, and this is, all of you please note down as well, huh? while we work it out. Let us say that this is your graph, and the cost between n1 and n2 is 1, between n2 and n3 it is 6, this is 2, this is 3, and this one is 4. So in distance vector routing, I already told you that every node has to maintain the routing table. So this routing table is going to have 3 fields. So one is the destination, right? One is the destination, it is then the distance and the next hop. So that means that from n1 you can go to n1, so it's basically the same node, so n1 to n1, n2, n3, n4, n5, right? So excuse my drawing over here, I am trying to draw in a platform where I cannot see, right? So I'm just looking at the screen and drawing. So yeah, so like this, basically, every table, every node is going to also have its destination, then distance or any cost you talk about, right? And the next hop. Same thing for this one. Okay, node 2. So here also n1, n2, n3, n4, and n5. Here also, destination, distance, then next hop, right? Same routing table, distance vector table. Then we are going to have here as well. Let us draw. So let me write down n1, n2, n3, n4, and n5. Here also destination, distance, and next hop. So once again, just to give credit to the source, I mean, this is not my own example, I have taken it from elsewhere. So just wanted to make sure that I do not take credit for something that I have not done. So this is for node 4, and node 3 also the destination, distance, and what the next hop, n1, n2, n3, n4 and n5. Okay. So do you understand what it means? So it means that every node is going to store this routing table or forwarding table. So this one is going to do, n2 is going to do, n3, n4, everybody has this table with them. So in distance vector routing, you need to understand few things. So number one is that the topology, every node topology, for application of distance vector, the topology should be known to the nodes. The topology of the network should be known to the nodes. This is one thing. Second thing that needs to basically we need to understand is how do you know the topology? So every node initially doesn't, initially it knows only the information about the immediate neighbors. So how does it know about the immediate neighbors? Through the exchange of something called the hello message. Through the exchange of the hello message, basically to know the neighbors. And over time it will take passes, it will take different passes to basically share this neighbor information that it has learned from its immediate neighbors. And over a period of time, everybody in the network is going to have this information about every other node. So now we once again, we start with this thing. We start with a network like this. Everybody has noted down this one. So we start with a network like this, and then what are we going to do? So first of all, so we need to share the routing information with the neighbors, right? So initially, think of it this way, that initially if you think of node 1, right? If you think of node 1, so you see that you are building this routing table for node 1. So for node 1, okay, to node 1, right? So this is for node 1, routing table of node 1. So you see that n1 to n1, what is the distance? The distance is 0. What is the next hop? Next hop is n1. Now n1 to n2, what is the distance? n1 to n2, what is the distance? 1. And what is the next hop? Next hop is n2. Like this, n3, n1 to n3, see n1 to n3. Remember that n1 cannot see n3, n1 can see only n2. So initially n1 cannot reach n3. So what is the distance? Distance is what? Infinity. And what is the next hop? Next hop we do not know because n1 doesn't know what is n3. So same for n4 also, and same for n5 also. Now look at n2's routing table. So n2 to n1, the distance is what? 1. What is the next hop? Next hop is n1. So this is for n2, right? This is the routing table for n2. Now n2, what happens? Now why it is happening like this? ठीक है. So whatever, so there is some problem. So anyway, so from n2 to n2, what is the distance? Distance is 0. And what is the next hop is n2. So n2 to n3, n2 to n3, next distance is 6, and the next hop is what? n3. n2 to n4, this is going to be what? n2 to n4, n2 cannot see n4, so infinity, and we do not know what is the next hop. And n2 to n5, n2 to n5, this is 3 units, right? So this is 3 units, and what is the next hop? Next hop is n5. So like this you can do for let us say let us do one more. So let us do it for this guy over here. Let us do it for this one. So this one it is going to be for n3, right? So routing table for n3. So here basically it is going to be n3 to n1 is going to be n3 to n1 is going to be infinity. This is not there. Then n3 to n2 is 6, and this is n2. Then this is going to be 0. This is going to be n3. This is going to be 2, and this is going to be n4. This is infinity, and this is going to be this thing. So like this, because I already have worked it out, let me also fill it out for you, so that you all can also go through at your leisure. And this is n5. And now let us the final one, this is for n5, right? For node n5, n5 to n1 is going to be infinite. This thing 2 will be 3, and n2 again infinity. This one 4, n4, and 0, n5. Is this clear? Anybody has any doubt? Because now if you do not understand anything, do not feel shy. If you have any doubt, ask, because I can clarify, and then we need to proceed further. Everybody is with me? Any question? Okay. Now what has to be done? So we have built the initial routing tables, the routing table entries in this manner. So what is directly observable, what is not, based on that we build this, right? As the next step, you need to share, okay, in the next round, what needs to be done? You need to share this routing table information. Actually, you do not share the routing table information, you share something, I will tell you. So you share something called the distance vector. You share the distance vector only with the neighbors. You share only the distance vector information with the neighbors. So this is very important. You share distance vector. Now the question is, what is the distance vector? So the distance vector is only this distance column, okay, only this distance column in this whole table. So the distance vector for node n1 is 0, 1, infinity, infinity, infinity. For node so for node n2, what is n2 here? The distance vector is going to be what? 1, 0, 6, infinity, and 3. So you see that node 2 is going to share its distance vector with node n1, and likewise n1 is also going to do the same. Okay, so after the first round, these distance vectors are going to be shared with the immediate neighbors. So because of this sharing, at node n1, at this node n1, what will happen? N1 now has access to this particular distance vector, which is 1, 0, 6, infinity and 3. It has access to it. So what it will do, at N1 it is going to revise its own routing table. So at N1 what will be the revised routing table? The new routing table of N1 will have the entries updated like this. So at N1, so let us first write down all the nodes in N1, N2, N3, N4 and N5, right? So what it is going to do? It is going to take that distance vector from N2, okay, and it is going to update its own routing table. It's going to update its routing table. N1 is going to do. So because of which the new routing table that you are going to get is going to have these updated distances like this: 0, 1, 7, infinity and 4, right? And N1, N2, N2 and N5. Now the question is, you might ask, like, how do we get this thing, right? Let us try to understand, right? So if it was a blackboard, it would have been easier because I do not have to run back and forth. So let us say that we talk about so this one is clear, this one not a big deal. Now let us look at how we got this new routing table. The distance to N2 is 1, and so how do we get? So for this one, you see that N1, so we are talking about N1, right? So node N1. Now node N1, so let us say that node N1 to N2, either we can go like this, okay, which will cost 1. N1 to N2 is 1, right? We already know, node 1 knows. And then you are getting this cost information from N2, that N2 from that distance vector table, you get N2 to N2, the cost is how much? Cost is 0. Okay, so the total cost from N1 to N2 is the sum of this. So N1 to N2 is, this is what N1 already knew, and this is what the information that N1 has got from N2. So it will be the sum of these two. So the total cost is going to be how much? 1 plus 0 equal to 0. You got it? So now this total cost, so this is how you get this 1. This is how you get this 1. Now what is, so now N3, so N3, how it will, what it will be, right? So again we have got this distance vector, so N2 to N3, basically N2 to N3, it can reach in 6 units cost, right? So N2 to N3, so let us try to understand how we got this 7. So we are saying that from 1 to 3, if we have to reach, right, it's going to be the, it is going to be through node N2 with the cost, total cost of 7. So how it is? So you see that we need to do it for, so from N1 to N3, you can do it through 2, because 2 has reported through its distance vector table that it can reach 3, right, through the cost 6 units, using the cost 6 units. So from N1 to N3 as a whole, then what will happen? N1 to N2 and then N2 to N3. Now for this, the cost N1 to N2, the cost is how much? Cost is already, N1 knows what is the cost. The cost is 1 unit. and n2 to n3 from the distance vector that was shared by n2, it now knows that the cost is 6 units. So what is the total cost? 1 plus 6 equal to 7 is the total cost. So this is what you write over here. And what will be the next stop then? Next stop is going to be 2. Right? So like this actually you perform for all the different other nodes also. Okay. So this is how you keep building the table. So let us take one more node and then we will close this. So let us say that at node n5, at n5, what is this n5? Let us try to understand what is this node n5. This node n5, if you look at here, this node n5, okay, this was the original routing table for n5. The corresponding distance vector is this one. So this is going to be shared all across. So likewise, n5 is going to get the distance vector of n2. n5 is also going to get the distance vector of n4. So it is going to use all of these information. So distance vector of n2 means what? That n2 says that in order to reach n1, I can do it in 1 unit. n2 says that in order to reach n2, I can do it in 0 units. n2 says that in order to reach n3, I can do it in 6 units. In order to reach n4, I can do it in infinite distance. Like that. So this is the interpretation, right? So that information is shared with n5. Likewise, here also this infinity, infinity 2, 0, etc. that information is also shared with n5. So it is going to use all of these plus its own distance vector in order to update its routing table over here. So at n5, what happens now? So at n5 is going to get access to the first distance vector, which is n2's distance vector. This n2's distance vector is going to have the entries 1, 0, 6, infinity, and 3. Exactly, what we have simply borrowed it from here. We have simply borrowed this distance vector. Likewise, from n4 also we are going to borrow this information because these are going to be shared with n5, right? So n4's table, n4's table. Just give me a moment. So n4's table distance vector, not table, the n4's distance vector is also shared with n5, and it is infinity, infinity, 2, 0, 4. Now n5 is now going to take this information and build its new routing table in this manner. It's going to build its own routing table in this manner. It is going to revise its routing table. It is going to update its routing table in this manner. So n1, n2, n3, n4, and n5 like before. So you see that we need to understand how we are going to populate this. So we need to understand that from n5, how can we reach n1? So we can reach from n5, so using all these distance vectors and its initial knowledge of the routing table that it has. N5 to n1, it can do it this way, that n5 to n2 with cost 3, and then from n2 it can reach n1 at the cost of 1. Okay, so what is the total cost now? The total cost is going to be 4 units. Either it can do this, or another possibility is that it could go from n5 to n4 at the cost of 4 units, and then from n4 to n1 with the cost infinity, the total of which is going to be how much? Infinity. So what it is going to do? It is going to take the minimum of these two. So what is the minimum? This is 4. So that is why the minimum of 4 and infinity, which is 4, is going to be updated in N5's revised routing table. So it says that from N5 to N1, if it has to reach, it can do so in 4 units of cost through the next hop N2. I hope that it is clear. Any question? Guys, please ask, because otherwise you will not be able to follow unless you ask. If you really have a question, if you do not have a question, it is well and good, but if you have a question, please feel free to ask. Is this clear? How we got 4 and N2? So likewise, basically, so this one is going to be 3 and N2. So N5 to N3 is going to be 6 units, N4 next hop. N5 to N4, it is going to be 4 units, next hop is going to be N4, and N5 to N5 is going to be 0, next hop is N5. This is going to be what? The new routing table of N5. Clear? Now, again, I'm giving you an opportunity. If you really have any question, please ask. Do not feel shy. Doesn't matter. Your marks are your marks. Your student, your friends will not get the marks, right? In case you lose your own marks. So it is better that do not feel shy. Do not think what your friends are going to think. Rather, you ask. So this is how basically, by the sharing of these distance vectors with the immediate neighbors. This is very important in distance vector routing. This distance vector is shared only with the immediate neighbor, not globally. So this is how basically these routing tables are updated over a period of time. So you see that if at any time, so you see that this is good, because if at any time any of these links, let us say that after some time this link breaks, right? Then basically N3's routing table will also be reflected, because it cannot reach initially, it cannot reach N4 directly. It is not its immediate neighbor as it used to be earlier, right? And then so same thing for N4 also. Then over time N3 will come to know how to reach N4 through couple of passes. It will come to know how to reach N4 through these nodes N2, N5 and so on. Okay, so this is how it can adjust to any kind of changes in the network. But now there is a problem, and this problem, it is called the count to infinity problem. It is called count to infinity problem. Let us try to understand what this problem is. This is a very famous problem in computer networks. So this problem occurs in the context of distance vector routing only. Let us say that this is your internet, and then so let us say that this is node B, which connects to the internet through cost 1 unit, and this is your node A, which connects to node B with unit cost, and then you have another node which is C. It connects to A with unit cost. Let us say that you have a scenario like this. Now you see that the main problem with distance vector is that it gives only the distance vector information, not the entire routing table, to its immediate neighbor. So each node in distance vector, it says that it will take to the internet, each node will tell that it can take to the internet with a certain cost, which is B can take to the internet with a cost 1 and so on, with a take to the internet with cost whatever, you know, so X, let us say that it is the cost is X, but it does not tell which node will help in the process. So in other words, you know, essentially you try to build it eventually, but you know, so when you are sharing the distance vector, only the distance vectors is shared, you know, not the exact, you know, not the whole routing table, like which is the next hop, etc., etc. Why do you do that? For good reason, actually. You want to cut down on the bandwidth consumption, right? The more you share, the more bandwidth will be unnecessarily eaten up. In order to, you know, conserve that, basically you cut down on what you are sharing. So you share only the distance vector. Okay, and this leads to the problem, which is this leads to updates in the costs to infinity when there is some problem in the network. What is this problem? Let us try to understand this. That initially, okay, so we'll come to this problem, but let us try to understand this, that we have this network, right? So what is actually done? So you see that, you know, so from B to B to the internet, the cost is initially 1. A to the internet, you know, A doesn't see the internet, so it is going to be infinity. C doesn't see it directly, so it is going to be infinity. So here I replaced with internet. You could have used some other node also, right? Doesn't matter, just for simplicity. Now in the next round, this is going to be what? Round 0. This is going to be, let us say that this is your round. So in round 0 like this, round 1, it is going to be what? Round 1, basically, you know, this information B is going to share with A. So now then A knows that, okay, A to B is 1 and B can reach the internet through 1. So now in round 1, basically, you know, A knows that in order to reach the internet, it can do so with 2 units, and this is basically 1 unit, and this is still infinity. In round 2, basically you continue, you get like this is going to be 1, this is going to be 2, and 2 plus 1, it is going to be 3. So this is how basically in rounds you try to get the updates, right? How to reach the different other nodes. This is what normally happens. Now everything is well and good, but then all of a sudden something happens. Let us say that all of a sudden this link, it breaks. Let us say that this link breaks between B to the internet. Now you see that now B is directly connected to the internet, so it knows that it got disconnected. So B, you know what it is going to do? B is going to update its distance vector. B is going to update its routing table and mark this connection to the internet to be infinity. So B knows where it is disconnected, so you know it is going to update to infinity. But A and C still do not know. A still thinks that it can reach with 2 units of distance, and C still thinks that, you know, it can do it with 3 units of distance. Now after some time, you know, this information is going to be shared with so A says to B that it can reach the internet with 2 units of distance, right? Now this is where the fallacy is. Now, A doesn't say to B that it can reach the internet through B. Had it told to B that it can reach through B, then B would have known that okay, already it is disconnected, so it cannot use that particular path. But only because only the distance vectors was shared, now A tells B that it can reach the internet through 2 units of distance. Now this is a problem. So same thing, so in the same way as B shares with A that it can reach the this thing with infinite distance. So here also A also does the same thing. And yeah, so here also so the same thing, A tells C that it can reach with 2 units of distance, and here also the same thing, so like this. So this process, you see, if you look down, after some time, in the next round, what is going to happen? In the next round, this is going to be 3, this is going to be 4, this is going to be 3. Again, you same thing you do. So this is shared, this is shared like this. Then in the next round again, it is going to be 5, 4, 5. This is going to be 5, 6, 5. Next round again, it is going to be 7, 6, 7, and so on. But you see that this is the problem. This is the problem. So like this, actually, this process, this continues to infinity. Okay. So you understood the problem. The problem was because only the distance vector was shared, that if something went wrong, like the link got broken, right? A doesn't know initially that this is what has happened. So it is going to take the minimum. So B is going to then take the minimum of how A can reach the internet and its infinite distance, and it is going to choose 2. But then A also cannot actually reach the internet because the link over here is already broken, and that information was not initially shared with. So these two problems basically, one is sharing only the distance information, and sharing with only the neighbors is causing this problem. Understood? So this is called this count to infinity problem in distance vector routing. How much time do you have? Can we complete the link state routing, the second type of routing? Students, can we take just 5 to 7 minutes more? 7 minutes, let us say. So 7 minutes I think we can afford, right? So any questions, students? Do you understand? Now let us start the other type of routing in the internet, which is called the link state routing. Now this link state routing was basically designed to overcome the problems, some of these problems that distance vector routing already has. So let us try to understand how link state routing basically works with the help of a small topology like this. This is your this is your R1, this is your router R2, this is your router R3, R4, R5, and R6. So in link state routing, you need to prepare and maintain, the link state, table. You prepare the link state table, and then you use hello messages. You need to share with neighbors. Okay, and the next thing that is characteristic of this link state routing only, unlike the distance vector routing, where these distances or the distance vectors were shared only with the neighbors, here this link state information is flooded all across the network. So this is the contrast, this is the difference between distance vector and link state basically. Here link state information is first of all preserved and for every node, and then you do a flooding, right, all across in the network. So every node is going to, as I said, every node is going to keep something called the link state table. Now this link state table is a simple one. So for link state, the link state table for R1, it is going to have this information. So few information followed by, it is going to have information like from R1. Oh, I forgot to give the edge weights, right? So 6, 3, 7, 7, this is 2, this is 9, this is 1, this is 8, and this is 4. Okay, again this example also I have borrowed from somewhere, so this is not my own, but that is not the intent. I mean, so basically we simply need to understand, right, irrespective of where we take these examples from. So R2 to so R1 to R2, you see from R1 to R2 the link cost is how much? 6 units, right? So 6 units. From R1 to R3 it is what? 3 units. So these information are shared, and also in the link state table basically, not only you maintain this information, but also you maintain something called the sequence number and this time to leave. So this time to leave basically, for a packet which doesn't end up looping, so throughout the network, so that it doesn't get lost. Basically, this time to leave of a particular this packet is used, right? So like this, actually every table also has the sequence number, TTL, and also this link state information, right? So link state information means like, so to it which node is connected through which link and how much is the cost, right? So every node basically maintains. So this node also, R3 also maintains the same thing, this link state table. R5 also maintains this link state table, exactly the same thing, sequence number, TTL, and this direct connection to which node, right? And then what it is going to do, this is this interesting part, right? So first of all, so let me tell you the steps. So first of all, the steps are going to be, first you prepare, the router or the node basically prepares its link state table, okay? Then it uses, so how does it prepare the link state table? The links basically, it can know through what? Through hello messages to the neighbors. Hello messages to the neighbors will tell you how much is the cost to reach the neighbor, right? So hello message to the neighbors. Then what? Then it uses flooding. It uses flooding. Again, as I said, like this flooding mechanism is the characteristic of this link state, this thing. And unlike in the distance vector, basically, only with the neighbors this information is shared. However, over here basically with the entire network, basically this information is is flooded. So basically each node floods the link state table to all nodes of what? The network, right? Now after this flooding has taken place, after flooding, what will happen? So so after flooding, basically R1 gets the global knowledge of the network. Like this, everybody else also does. Now then what happens is, you as a next step, you applies the Dijkstra's algorithm, because we are focusing on R1. So let us look at R1 only, Dijkstra's algorithm at R1. You apply this Dijkstra's algorithm at R1. And what does Dijkstra's algorithm do? It computes the single source shortest path, right, from it to all the nodes in the network. So Dijkstra's algorithm. So by applying Dijkstra's algorithm, you know what is the routing table going to be. So as part of that, if you now construct the routing table using Dijkstra's algorithm, okay, so all of you know Dijkstra's algorithm, everybody knows. You apply that, so you work it out, right? So you have learned in your algorithms course this algorithm. So then it is going to have entries like this, that destination, then basically this link state information or the cost basically, and through which node, So this is going to be the R1, R2, 5, R1, R3, 5, R1. I'm just giving you the final result, so please work it out yourselves, because I'm not going to teach you Dijkstra's algorithm, right? So all of you already know. So but you check and you verify that you are able to get it. R4, 12, and through R3, and then R2, then R5, 12 through R3, and R6, 12. Oh, sorry, not 12. This will be 16, and through R3, and then R5. So you apply this Dijkstra's algorithm, and then you know that every node, so router R1 knows that how it can reach all the other nodes in the network. Okay, this is your link state routing. So we are just few minutes over time. So yeah, so all of you please make sure that you understand, as I said, like these are very important concepts, and do not ignore at all, for exam sake at least. So distance vector, the problem with distance vector, the count to infinity problem, and also the link state routing protocol. So distance vector, link state routing, and the count to infinity problem for distance vector. Basically these things you should understand very well. I work it out yourselves, so please all of you verify yourselves that whether you are able to understand offline. You please do it and try to convince yourselves. Any question before we stop here? Okay, then thank you. We are going to end here now.